Good afternoon, everyone. I'm Shreya, one of the TAs for this course on Essentials of Data Science with R. And today I'll be talking about week 9 and week 10 lectures, predominantly week 10 lectures. But I'll briefly touch up or do a recap on one of the concepts that were discussed during week 9 lectures. So, without any further delay, let me get started. So, during week 9, we had also, apart from the distributions bivariate normal, chi-square, t and f, we also learned about sample means, sample variance, and distribution of sample means, and also we learned about a concept which is called convergence. Okay, so we got an idea behind the what do we mean by convergence, and we also got to know that there are several modes of convergence. So briefly, there are 4 modes of convergence, okay, and they are convergence in probability, convergence in distribution, convergence in absolute sure sense, absolute surely, and then also convergence in arithmetic. Alright, and out of these we discussed convergence in probability. Okay, so out of this we discussed this in details, convergence in probability. And what do we mean by that? If we have xn as a sequence of random variables, then we can say xn converges in probability to some random variable x as n tends to infinity if we can write probability modulus of xn minus x is greater than epsilon. This quantity tends to 0 as n tends to infinity for all epsilon greater than 0. Okay, or in other words, if probability xn minus x less than epsilon, this probability tends to 1 as n tends to infinity for all epsilon greater than 0. Okay, so what it means that as n is getting closer and closer, the probability that the difference between xn and the nth term of the sequence and the random variable it converges to, that probability that probability goes to 1, that it is very smaller, even less than epsilon, that goes to 1. All right, okay, this was the idea behind convergence in probability. And so let us solve one few sums to demonstrate this idea. Okay, so let's say you have any random variable such that xn follows exponential n. Okay, so then we have to show that this sequence of random variable converges in probability to 0. Okay, so then let us write limit n tends to infinity probability xn minus x is greater than or equal to epsilon. This we can write as limit n tends to infinity probability xn minus x this is xn minus x. Instead of x we can write here, since this is it is converging to 0 random variable, so we'll write xn minus 0 greater than epsilon. Okay, so this means limit n tends to infinity probability xn greater than epsilon. Now since xn's are all exponential, how does it exponential function look like? This looks like lambda e to the power minus lambda x for all x greater than 0 and 0 otherwise. Okay, so all x's are non-negative. So then this means we can write this as limit n tends to infinity probability mod of xn should be this thing. Okay, now probability xn greater than epsilon. So we know if we calculate the CDF of x, which follows an exponential distribution lambda, is, if x is how much, we can write it as probability x less than equal to x is 1 minus e to the power minus lambda x, where x is greater than 0 and 0 otherwise. Therefore probability x greater than x is 1 minus probability x less than equal to x, so that we can write as 1 minus e to the power minus lambda x, 1 and minus 1 cancels, e to the power minus lambda x. Okay, so this is the formula. So now we have probability x n greater than epsilon. So what can we write over here? So here we have probability xn greater than epsilon, where xn follows exponential n. Okay, so then this one would be e to the power minus, instead of lambda we'll have n, and instead of x we'll have epsilon. Alright, therefore limit n tends to infinity probability xn greater than epsilon is equal to limit n tends to infinity e to the power minus n epsilon. Now as n tends to infinity, this quantity goes to 0, so this will be equal to 0. So therefore what do we have? Probability xn minus x greater than lambda greater than epsilon, it goes to 0 as n tends to infinity, which implies xn converges in probability to x, where x is 0. Or you can write it like this: xn converges in probability to 0. Alright, so moving on. Here the question is, let x1, x2, xn or x3 be a sequence of IID uniform 0, 1 random variables. Now we are defining another sequence yn, which is the minimum of these n random variables. Then we have to state if the following is true or false, that yn converges to 0 in probability. Alright, so how do we do this? So xn follows uniform 0 1. So fxn, that is the CDF, fxn x can be written as 0 if x is less than 0, x if 0 less than equal to x less than equal to 1, and 1 if x is greater than 1. Okay. Now yn is the minimum of xn and y, x1 to xn. All of them range between 0 and 1. Therefore, yn will also range between 0 and 1. Okay. So now, if we want to write the CDF of y and y, this will be probability yn less than equal to y. This we can write as 1 minus probability yn greater than y. Now, if the minimum is greater than y, this implies that all other variables are greater than y. So this we can write as equal to 1 minus probability x1 greater than y, x2 greater than y, xn greater than y. Okay. Since minimum is greater than y, all of them should be greater than y. Okay. Now this one, x1 greater than y, x2 greater than y, xn greater than y, this one we can write as 1 minus probability of x1 greater than y into probability of x2 greater than y into probability of x3 greater than y into probability of xn greater than y. Why can we do that? Because it is IID, independent. Okay, identical and independent. This one we can do because x1, x2, xn are independent. Okay. So if two events are independent, probability A and B both are independent, then probability A intersection B is probability A into probability B. Same here also, we have x1 also greater than y and y2 x2 greater than y and xn greater than y. So in essence, this is intersection. Since all are mutually independent, we can write it as a product of their probabilities. Okay. So once we have that, for this one, we can write this as 1 minus probability x1 greater than y means what? This means 1 minus fx1y. Fx1y means what? Probability x1 less than equal to y. So 1 minus will give you this. This implies 1 minus f of x2y into 1 minus f of x and y. Okay. Now since xi's are identical, we can write this as 1 minus f x1y to the power n, or let us write this as, yeah, okay. So now x1 follows a uniform 0 1. So this means probability xn less than equal to x. Okay. So 1 minus this one, f of x1y, this will be So since y also lies between 0 and 1, we can write this as 1 minus between 0 and 1, this is x. So instead of here we have fx1y, same as fx and y. So here we'll put, since it is between 0 and 1, we'll have to put y. So here we have fx1y as y. This will be 1 minus y whole to the power n. Okay. So therefore, this is f, y and y. So the CDF of yn is f of y and y. This is 0 if y less than 0, 1 if y greater than 1, and 1 minus y to the power n if 0 less than equal to y less than equal to 1. Alright, now we have to show yn tends in probability to 0. This is to show. Okay, so what we have to show? We have to show limit n tends to infinity, probability mod yn greater than epsilon is equal to 0. Okay. Alright. So this one we have to show for all epsilon greater than 0. So since yn also lies between 0 and 1, this is also always a positive quantity. So we have to show limit n tends to infinity, probability yn greater than epsilon is equal to 0. Alright. So now here the thing is, probability yn greater than epsilon is equal to 1 minus probability yn less than equal to epsilon. So which means 1 minus f of yn epsilon. This means what? 1 minus f of yn epsilon is how much? 1 minus 1 minus y to the power n. 1 minus epsilon to the power n. So this is 1 minus epsilon whole to the power n. Alright. Okay. So now if epsilon belongs to range 0 and 1, then we can write that this quantity will be a fraction. Okay, if epsilon is equal to 1, this will be 0, exactly 0. If it is 0, then it will be 1. But for epsilon belonging to this range, which is 0 to 1, we'll have this thing will go to 0 because it's a fraction. Okay, as n tends to infinity and given epsilon is belonging to 0 and 1. Alright. This is 1 inclusive. Even if it is 1, then it will go to 0 definitely, and if it is greater than 0, then also it will become something, it will become a fraction, and to the power n will go to 0. So for this specific epsilon, this yn converges in probability to 0. Alright. Okay. So during week 10, we learnt about unbiasedness. We learnt about how to evaluate efficiency of estimators, and what do we do, how we should select our estimator which gives better in terms of performance, and why is there a need for statistical inference. So before moving on to the questions, let us briefly brush up our concepts on week 10 lectures. Okay. So week 10 recap. All right. Okay, so first we discussed what is the need. What is the need? Suppose we have a population. Okay, this is the population, and we have some parameter of interest theta. This is our parameter of interest. Now we want to know the value of theta. Most often than not, it is not possible to calculate the whatever theta is based on from the entire population. So what do? We take a subset from this population. This is a subset. Okay, and then this one we call it as a sample, and we get theta hat, which is an estimate from the sample, and then we find out, we judge the efficacy or goodness, rather I would say, not efficacy in the truest sense of term. We just judge, is it a good approximate for theta. Okay, is it good or is it bad? If it is good, then how confident are we that this is good? Then these are all the things that we usually do. Okay, and this sample is usually a representative of the population. Okay, also we learnt about what is the difference between parametric and non-parametric inference. Okay, so parametric means that the parameters have an underlying distribution. Okay, and the inferences that are based upon this assumption that the underlying distribution is known through, it can be specified with the help of these parameters, those sort of inferences are called parametric inferences. Okay, and if we do any parameter free inference, where we are not assuming that our parameter of interest has an underlying distribution, Okay, that sense it is called a non-parametric inference. Okay, and then we learnt about estimators. Okay, we learnt about estimators. Specifically, we learnt about point estimators. Sorry. Okay, so point estimators are what? They give, there are two kinds of estimator, point estimators and interval estimators. So if this is my population of interest, let's say P, and here theta is my parameter, I want to specify what the value of theta is. If I say that theta is equal to 5.23, then this is an example of a point estimate. Okay, but if I say theta hat belongs to 4.27 and 5.23 in this interval, then this bound that we are giving, this is the interval estimate. Okay, and we usually give this interval estimate with a certain confidence that theta is contained in this interval with a probability of 95%. Okay, this is how we phrase it. Theta is contained. Okay, not that theta lies between, the estimate of theta is contained between this one, this lower bound, and this upper bound. So if we specify such intervals, then these are the interval estimators. Okay, now then we learnt about some properties of point estimator. And in the context of estimator, we learned the term statistic. Now, what is a statistic? This is a function which is solely based on observations and is free from any unknown parameter. So, in other words, if your sample is known, statistic Tx is completely specified. Okay, now when we are talking about an estimator, what do we mean? If let's say I say that Tx is an estimator of theta, then we write that theta hat equal to Tx. Okay, so whenever we are putting hat above any unknown parameter, that means we are getting an estimate. Okay, so we are estimating theta with the help of Tx. Okay, and Tx is always the estimated value from realized sample. Okay, now the problem is, since the estimator is from a realized sample, So let's say this is my population P, this is theta of interest. Now if I draw this sample, then I am getting a theta 1 hat. If I draw a sample from this location, I am getting theta 2 hat. So theta is fixed in the population, but my estimate will depend on the sample that I am drawing from the population. Okay, so since each sample can lead to a different estimate of this theta, we would want certain properties to hold. We would want theta to be as close to theta as possible, and we would want very less variability around theta. Okay, so these are some basic properties that we want our point estimators to have. So to list it out, some good properties are of any estimator. So some good properties are if it is unbiased. Okay. Second good property is it should be efficient. Okay. Third good property is it should be consistent. Fourth property is it should be sufficient. And fifth property is completeness. Okay. And these are all separate. Having this does not imply this, having this does not imply this. Okay, like there may be overlaps, well, not exactly true overlapping sense of terms, but a few might seem similar, but these are all independent properties. Having one does not imply that you would have the others also. Okay, if you have it, it's good, but there is no guarantee that this will hold true. Alright, so the first thing that we want to know is unbiasedness. So what is unbiased? So if Tx is an estimator of theta, then theta hat equal to Tx. And expectation of Tx, if this is equal to theta, then we say that Tx, the statistic, is an unbiased estimator of theta. So if expectation of Tx equal to theta, then we say that Tx is an unbiased estimator of theta. So what do we mean by unbiased? So we mean to say that Tx should be close to the true value of theta in some sense. Okay. If it is not, if expectation of Tx is not equal to 0 or not equal to theta, then we say Tx is a biased estimator of theta. Now we are saying it biased. How biased is it? So we calculate bias Tx equal to expectation of Tx minus theta. This term is the bias of estimator Tx. Okay. The next thing that we want is efficient. Now, how do we quantify efficiency? So, efficient means that the variance should be small. In some sense, should be small. So as I was mentioning, if you have a population, drawing different samples would result in different estimates of theta. Now you would want that variability to be very low. You want the estimate of theta to be very close to the actual value, and you don't want too much of variance around your estimates. Okay, if the variance is contained, there is not much spread of the estimate of the variance of your estimator. If it is low, then we can in some sense say that okay, this is a good estimator. It is very very close in some sense to the actual value, and the variability is very very low. Okay. So now we learnt about a term called mean square error, which is actually expectation of theta hat minus theta whole square. And for this one you could write it as variance of theta hat plus bias of theta hat whole square. Okay, so since bias and variance both characterize any goodness or goodness of any estimator, both of these are in some way captured by the mean square error. Okay, MSE is nothing but mean squared error. Now it turns out that these behave in a very complementary manner. So what I mean to say is that it is not always possible to control both variance and bias. Not always possible. Okay, if you want to minimize both simultaneously, that is not going to happen. So that there's always a trade-off between variance and bias. Okay, so that we called as the bias variance trade-off. This exists because it is not possible to simultaneously reduce or minimize both variance and bias. Okay, so whenever we are talking in terms of efficiency, where is the cursor? Yeah, so whenever we are talking in terms of efficiency, we say let us have, let's say, two estimators, theta 1 and theta 2 hat. So if variance of theta 1 hat is less than variance of theta 2 hat, then we can say that theta 1 hat is more efficient. Okay. Similarly, if mean squared error of theta 1 hat is less than MSE of theta 2 hat, then we can say that okay, theta 1 hat is more efficient. Okay, but that we need to be aware of. So let's say, since this is parametric, this is a parametric estimation, theta will belong to some parameter space which is also theta. Okay, so if let's say variance of theta 1 is less than or equal to variance of theta 2, and variance of theta 1 hat is less than variance of theta 2 hat for at least one theta belonging to this space theta, then we say that theta 1 hat is more efficient than theta 2 hat. Similarly, if MSE is less than equal to theta, for theta 1 hat is less than equal to theta 2 hat, and MSE is strictly less for at least one value of theta, then we say theta 1, same here, for at least one theta belonging to this parameter space, then we say theta 1 is more efficient. Okay. Now, how do we calculate the relative efficiency? Okay. So, efficiency of theta 2 hat to theta 1 hat is given by, efficiency is 1 by variance. So, here we will have 1 by variance theta 2 hat, and here we will have variance of theta 1 hat. Okay. So, this is in terms of variance. In terms of MSE, if we write, then efficiency of theta 2 hat relative to theta 1 hat would be same thing, 1 by MSE theta 2 hat, 1 by MSE theta 1 hat. Okay. And if efficiency is less than 1, then we say that theta 2 is so if this is less than 1, then MSE of theta 1 hat will be less than MSE of theta 2 hat, and that means that theta 1 is more efficient than theta 2. If efficiency is greater than 1, then it means theta 2 relative to Q1 is greater than 1. It means efficiency of Q2 is more than efficiency of Q1, because the MSEs of the corresponding variances are low. Alright. So, usually the most popular choice is to choose an unbiased estimator with a lower variance. Okay, but sometimes the biased ones are preferred because they have smaller mean square errors. Okay, because if you remember, MSE combines both variance and bias. Alright. Now, also we learnt about another term, that is the MVUE, minimum variance unbiased estimator. This is minimum variance unbiased estimator. So, if this is a class of all unbiased estimators, if this is the class of all estimators, let's say, of theta, a subset of that will be the class of unbiased estimators of theta. Alright, among which, okay, the one with the, let's say, this point, if this has the smallest variance, then this is the MVUE. Okay, and this is in some way the best estimator. Okay, because it is very close to theta in expected sense, and it is attaining the minimum variance that is possible. Alright. Now, Apart from this, so we see that whenever we are providing some estimate, okay, let's say 5.23, you would usually see a term like this, 0.02, something like this. This is your standard error, okay, of your estimate, and it in some way gives the precision of your estimate. Okay, so standard error is nothing but square root of variance of your estimate. All right. Okay, so we learned this, we learned efficiency, we learned standard error, we learned okay, so another thing that we learned is the Cramer-Rao lower bound. Cramer-Rao lower bound, or CRLB. Okay, so what does this lower bound provide? This lower bound provides a variance for a lower bound for the variance of any unbiased estimator of some function of the parameter of interest. So let's say theta is my parameter of interest, which is unknown in the population. I am drawing samples to get to know more about theta, and I want to find out some desired function. What should be the value? All right. So then let's say if del x is an, if expectation del x equal to g theta, this means that del x is an unbiased estimator of g theta. Okay, and if let's say the lowest variance of del x, if this will always be greater than or equal to the Cramer-Rao lower bound. Okay, and if it attains the Cramer-Rao lower bound, then this is the best estimator among the class of unbiased estimator. Okay, so closer it is, the better the estimator is. All right, and what was the formulation? We found that this variance, if we have x1, x2, xn and IID random sample from this distribution x given theta, then variance of, let's say, del x, which is a function of these random variables which will be realized. Okay, so this one will be greater than equal to g prime theta whole square by ne del theta of ln f x given theta whole square. Okay, and this expectation of this thing, this denominator, this is actually what you call as Fisher information. Okay, this entire thing, the one circled in blue. All right. Okay. So we see that efficiency of an unbiased estimator, so efficiency of, let's say, delta x is usually given by CRLB by variance of delta x. Okay, how does it compare with respect to the lowest variance that it can attain? All right. Okay. So with this, let us move on to the questions. Okay, before the questions, we also learned briefly about CLT. Okay, so we also learned about CLT, or the central limit theorem, which says that if x1, x2, xn are randomly distributed, then summation xi will follow asymptotically a normal distribution. Okay, and if we do summation xi minus n mu by sigma root n, or in other words x bar minus mu by sigma by root n, this follows asymptotically normal 0, 1. Okay, so this will hold if n is very, very large. Alright, so now let us move on to the problems. So the question is, suppose that an instructor assumes that a student's final score is the value of a normally distributed random variable So let's say, suppose that an instructor assumes that a student's final score is the value of a normally distributed random variable following normal mu sigma square. This will be mu and sigma square, pardon me. Okay, this will be mu and this is sigma square. If the instructor decides to award a grade A to those students whose score exceeds mu plus 2 sigma, then the proportion of students getting grade A would be how much? Okay, so grade A will be awarded to students getting whose scores exceed mu plus 2 sigma. Okay, so then we want the probability x is greater than mu plus 2 sigma. Okay, students final score and x follows normal mu sigma square. So this one we can write as probability x minus mu by sigma will be greater than 2. Okay, so now x minus mu by sigma will follow a normal 0 1 distribution. Therefore, this will be p norm 2 comma lower dot tail equal to false. Or in other words, you could just write p norm 2, or you can just do a 1 minus of, sorry, 1, where is this? You could do 1 minus p norm 2. Alright. Okay. So, moving on. So here they are saying, suppose that two fair dice are tossed 1200 times. Let x denote the number of times a total of 8 occurs. Then x has a binomial distribution with parameters n equal to 1, 2, 0, 0 and p equal to 1 by 6. So find normal approximation to probability 90 less than x less than 210. Okay, so here what do we do? So x follows binomial 1, 2, 0, 0 and p is given 1 by 6. Okay, alright. So I hope you understood how you got this 1/6. So 8 can happen if it is 2, 4, 4, 2, 3, 5, 5, 3 and 4, 4. Any other combination gives a total of 8. 1, 5 is going to give you, so 1, 6 is going to give you this. 2, 5, 4, 2, 3, 5, 5, 3, 4, 4 in the first die and also 4, 4 in the second die. So 6. Okay, so 6 into 1, 6 into 1, 6. So this would be 1, 6. Okay, that's how you get the probability. Alright, so x is a binomial distribution with parameters 1, 2, 0, 0, p equal to 1 by 6. Then find the normal approximation. So we want probability 190 less than x less than 210. So now since n is large, we can apply the normal approximation. So for that, what do we need? Expectation of x is how much? This is np. Okay, so this will be 1200 into 1 by 6, that is 200. And variance of x is how much? Np into 1 minus p. So this will be 1200 into 1 by 6 into 5 by 6. So this will be 200 into 5 by 6. That would be something around 200 into, let's say, 5 by 6. That will be 166.67. So this will be 166.67. Alright. So now probability 190 less than x less than 210, we can write this as probability 190 minus 200 by root over 166.67. This is actually x minus np by root over np 1 minus p less than 210 minus 200 by root over 166.67. Alright. So this one is asymptotically following a normal 0 1 by CLT. Okay. So then we can write this as equals to probability minus 10 by root over 166.67 less than equal to z, or strictly less than z, less than 10 by root over 166.67. Okay. So we can write this as p norm 10 by root over 166.67 minus p norm minus 10 by root over 166.67. We'll find out what the answer is. So we'll write p norm. So you understood what is happening here. This is z, symmetric about 0. This is plus 10. This value a. This is b. So a is here and this is minus a or b. So we are taking this area total and subtracting this area. Okay. So p norm 10 by square root of 166.67 minus p norm of minus 10 by square root of 166.67. So that is 0.56 something. Okay. So then this comes to 0.56. Alright. Okay. Okay, somebody has joined. Okay. Hello, would you want to ask anything or say anything? Ma'am? I'm not able to hear you, ma'am. Still nothing. Yeah, for a brief moment, I think you were audible. But now it's still, again, it's gone. Can you please type it in chat box? Absolutely not audible. I hope my screen is visible to you. You're not audible, ma'am. Can you please type in chat box if you have any doubts, queries? I can see that your mic is unmuted, but I'm not able to hear anything. Right. So, I'm not able to hear anything from you. I'll just move on. If you have anything, please type it out so that I'm able to understand. Okay. So, let's say we consider the amount of coffee dispensed by a coffee machine to be a random variable. Okay. So, this machine dispenses on an average 100 ml. Okay. Hello, ma'am. Now I'm able to hear you. I think. Is there anything, any specific query? Are you able to see my screen? Okay. So the machine dispenses on an average 100 ml coffee with a standard deviation of 16 ml. Okay. So if x follows some distribution, okay, on an average mu is 100 and sigma is 16. So find the probability that average coffee dispensed in a random sample of size 64 is at least 105 ml. Okay. So average coffee dispensed, our variable is, let's say the variable is average coffee dispensed. So that is essentially x bar. So we have to find out that in a random sample n equal to 64, probability x bar greater than 105. Okay, now we'll assume that x follows a normal mu sigma square. Mu is given by 100. Oh, I was unmute. Hello? Hello? Hello, ma'am. Are you able to hear me? See my screen? Alright. So mu was 100 and sigma was 16. Okay. So x bar follows normal mu sigma square by n. Okay. So probability x bar greater than 105, I can write it as probability x bar minus mu by sigma by root n greater than 105 minus 100 by sigma is 16 and n is 64. So root n would be 8. So this is actually a standard normal. Okay. So z greater than 5 by 2. So this will be 1 minus, so this will be probability z greater than 5 by 2. So this would be p norm 2.5, mu equal to 0, st equal to 1 and lower dot tail equal to false. So if we do this, how much do we get this as? P norm 2.5. By default it will take mu 0 1, lower dot tail equal to false, then that is 0.006. This is equal to 0.006. 0.006. Okay. Alright, shall I move on to the next one? Okay. So the question is, an insurance company has 10,000 automobile policyholders. If the yearly claim of a okay, thank you. Alright. So an insurance policy company has 10,000 automobile policyholders, and if the if the yearly claim is said to be a random variable with mean 180 and standard deviation 16,000. Probability that the total yearly claim exceeds 4.8 million. Okay, so let's say xi is the yearly claim of ith policyholder. Okay, so we have a random sample x1, x2, xn, all following that, let's say, random distribution, normal distribution. with mean 180, and this is the variance. Standard deviation is this one. Standard deviation 16,000. Okay. So then total claim will be summation xi. So that follows normal. So summation xi, this will be n mu, and this will be n sigma square. Okay, since they are independent. Okay, x1, x2, xn, all my policy does not depend on person 2's policy. We are all independent. So that's why summation xi will follow normal n mu and n sigma square. Okay, so n mu is how much? This is n into 180. Okay, and n sigma square is n into 16000. So this will be 180 and then 4 zeros, and this is also 16000 and then 4 zeros. So now the question is, what is the probability that the total yearly claim exceeds 4.8 million? So let y equal to summation xi. We have to find out probability y greater than 4.8 million, which means 4.8 into 10 to the power 6. This is probability y greater than 48,000,000. So this means probability y minus, what was the mean? Mean was 180 and then 0000. Okay, so this probability is 180,000,000 divided by square root of 16,000 into 10,000. Okay, this one will be greater than 480,000,000 minus 180,000,000 by square root of 160,000,000. Okay, so whatever this value comes up, that we have to do a P naught. Okay, so this will be probability y greater than, this is n mu by root n sigma. Oh, okay, so this is one mistake that I did. This one is actually n sigma square, so we have to divide by root n and sigma. So we have to divide this by so this should be root n into sigma. Now sigma is given as 16,000. Okay, and n is 10,000. So root n sigma will be 100 into 16,000. Okay, so this will also be 100 into 16,000. So this will be greater than 300 into 0000 by 16,000 into 100. Okay, so 5 zeros will cancel, so we will have probability z greater than 30 by 16. All right. So then this will be P naught 30 by 16 lower dot tail equals to false. So we'll just type out here P norm P norm 30 by 16 lower dot tail equal to false. So that will be 0.03. So this will be 0.03. Okay. Alright. Now let us move on to the next one. So the question says that the ideal size of a first year class at a particular college is 150 students. The college, knowing from past experience that on an average only 30% of accepted admission will actually attend, uses the policy of approving applications of 450 students. Compute the probability that more than 150 first year students attend this college. Okay, so how to solve this? Alright, so the college has admitted n students, okay, and it assumes that P equal to 30% will attend. So if X is the number of students who attend, then X follows a binomial with NP, okay, where this is binomial 450 and 0.3. Okay, so then now the probability is, compute the probability that more than 150 first year students attend this college. So probability X greater than 150. Alright, so this one we can write as probability X greater than, we'll apply that continuity correction, 150 minus 0.5. Alright, so this one we can write as probability X minus NP by square root of NP into 1 minus P is greater than 150 minus 0.5 minus 450 into 0.3 is how much? This is NP. And NP into 1 minus P is 450 into 0.3 into 0.7. So I'll just stop my screen share. Okay. Okay, yes. Standard deviation in the previous one was 16,000, so variance would be square of 16,000. Yes, that's true. Okay. So I wanted 450 into 0.3. This is 135, and 450 into 0.3 into 0.7 is 94.5. So here we have to write this. So this will be probability X minus NP by root over NP into 1 minus P greater than 150 minus 0.5 minus 135 by root over, what did we get there, nt into n1 minus p, that is 94.5. Okay, so let us compute what this comes out to be. So 150 minus 0.5 minus 135 divided by square root of 94.5. This is 1.49. Okay, let's say this is my z, and what do I want? I want probability greater than this value. So this will be p norm z lower dot tail equal to false. So we'll just type this p norm z lower dot tail equal to false. So this is 0.06. Alright, so the answer is here 0.06. Is it okay? This will be option A. Okay, one thing is that whenever you are doing binomial to normal or Poisson to normal approximation, please use this continuity criteria. Alright, okay, so let us move on to the next one. So this question says that suppose t is calculated from sample values x1, x2, xn to estimate theta, which of the following is a statistic? So statistic is what? That is based on a realized sample, and this should be devoid of any unknown quantities, or rather unknown parameter. So for this one and this one, these are not statistics because theta is already involved in their formulation. You cannot have any unknown quantity in the in any statistic. A statistic should be solely based on the realized sample or observations. It should be solely some function of xi and xi only, nothing else. It could have some constant but not anything unknown. Okay, so then this is actually a statistic. Is it okay? Alright, so let me move on to the next one. Alright, okay. So let x1 xn be a random sample from the probability density function. This determine which of the following is true for sample mean about its bias. Okay, so sample mean is an unbiased estimator. Is it a biased estimator, or if the bias can be determined or not, that we have to see. Alright, so expectation of xi, any xi, is how much? This is actually, since the value of x ranges from delta to infinity and 0 otherwise, this will be delta to infinity x into e to the power minus x minus delta dx. Okay, so here if we write y equal to x minus 8, dy is dx, then this is 0 to infinity, x is y plus 8, sorry, y plus delta e to the power minus y dy. Alright, So then we have to solve 0 to infinity y plus delta e to the power minus y dy. So this is 0 to infinity y e to the power minus y dy plus delta 0 to infinity e to the power minus y dy. Okay. Now this, if we assume that y follows an exponential distribution, this is actually 1 because this is the PDF, and 0 to infinity PDF will give you 1. So this is 1 plus delta, this is e to the power minus y minus, we have to evaluate from 0 to infinity. So this is 1 plus delta into e to the power minus infinity is 0, minus of minus e to the power 0 is 1. So this is actually 1 plus delta, which is not equal to delta. Okay. So therefore sample mean is a biased estimator of delta, and the bias, and how much is the bias? Bias is expectation of sample mean minus delta, which is 1. Okay, so this bias can be calculated, and this is actually 1. Is it clear? Any questions? Okay, if not, then I'll move on to the next one. Okay, so here they are saying let x1, x2 be independent random variables with mean mu and variance sigma square. Suppose there are two estimators of mu, beta 1 x1 plus x2 by 2 and beta 2 x1 plus 3x2 by 4. Then we have to compare if both are biased or unbiased and the variance of these two. So let us first find out whether they are biased or not. So expectation of beta 1 is equal to expectation of x1 plus x2 by 2. So this is expectation of x1 by 2, or half if I just take common because this is a constant, half of expectation of x1 plus x2. So this is half of expectation of x1 plus expectation of x2. This is half of mu plus mu. This is mu. So B1 is unbiased. Okay. Beta 1 is unbiased. Expectation of beta 2 is how much? Expectation of x1 plus 3x2 by 4. This will be 1 by 4. Expectation of x1 is mu plus 3 expectation of x2 is 3 expectation of 3 mu. So this is also 4 mu by 4. This is also mu. So both are unbiased. Okay. So this is either A or B. Now we have to find out which one has lower variance. Okay. So let us calculate the variance of beta 1 and beta 2. Okay, so here variance of beta 1 equal to what? Variance of x1 plus x2 by 2. So this would be 1 by 4 because when constant comes out it is usually squared. 1 by 4 variance of x1 plus x2. Now since they are given that they are independent random variables, we can write it as 1 by 4 into variance of x1 plus variance of x2. No covariance is involved. Sigma square, 2 sigma square by 4. This is sigma square by 2. Alright. Now variance of beta 2 is variance of x1 plus 3x2 by 4. So this will be 1 by 16 variance of x1 plus 3x2. So that will be 1 by 16 variance of x1 plus 9 variance of x2. Okay. So this will be 10 sigma square by 16. Okay. So here we can see 10 sigma square by 16 is greater than sigma square by 2. Is greater than sigma square by 2. 2 into 8. Alright. So therefore variance of B2 is greater than variance of B1. So the correct answer is this one. Okay. Is it clear? Any doubt? All right. Okay. So let's move on to the next one. Here they are saying if x1, x2, xn be a random sample from a population with normal distribution with population mean mu and variance sigma square, assume sigma square to be known and let x bar is be this thing, then an unbiased estimator of mu square is how much? Okay. So let us find out expectation of x bar square. Since x bar square is common over here, let us find out expectation of x bar square. Now x bar follows normal, mu and sigma square by n. Alright. If xi's follow normal mu sigma square, then x bar will follow normal mu sigma square by n. This we have done previously also. Okay. Since it's a sum of normal distributions, a linear combination of normal will follow normal, and if we just do the expectation and variance assuming all are independent, then this is what we get. Now expectation of x bar square, we can write this as variance of x bar plus expectation of x bar whole square. Okay. Then this is actually sigma square by n plus expectation of x bar is mu square. So if we write this expectation of x bar square minus sigma square by n equal to mu square. Now given it is asked to assume sigma square to be known, then our Tx is actually this thing, x bar square minus sigma square by n, and expectation of Tx is fully specified assuming sigma square to be known. Given the sample x1 to xn, we will get the value of Tx completely. So expectation of Tx is equal to mu square. So given sigma square is known, x bar square minus sigma square by n, this one is an unknown estimator of mu square. Is it okay? Okay. So then let us move on to the next one. Now suppose we have a sample of size 3n from a population of x with mean mu, variance of sigma square. Suppose there are two estimators of mu, 1 by 3n summation 3n xi and 1 by 2n summation 2n xi. Then we have to find out if both are biased, unbiased, or what it is. So let's say this is not b1, actually this is mu1 hat. Okay, this is mu1 hat and this is mu2 hat. So expectation of mu1 hat is as usual 1 by 3n summation I equal to 1 to 3n expectation of xi, that is mu. So this is 1 by 3n into 3n mu, so this is mu, and expectation of mu2 hat is the same 1 by 2n summation I equal to 1 to 2n expectation of xi, so this will be 1 by 2n into 2n mu, that is mu. So both are unbiased. We would either have 1 A or B. Now the next part is to find out the variance. So similarly, we will calculate the variance. Okay. So variance of mu1 hat will be 1 by 9n square summation of I equal to 1 to 3n variance of xi. Since xi's are, we have a sample, we assume it to be a random sample. Okay, that means IID. So this means 3n by 9n square, that is 1 by 3n. And variance of mu2 hat is 1 by 4n square summation I equal to 1 to 2n variance of xi. So this will be, this is actually sigma square, sorry. So this will be 2n by 4n square sigma square. So this will be sigma square by 2n. So now sigma square by 3n is less than sigma square by 2n. Therefore, variance of mu1, this is the correct answer. Variance of mu1 hat is less than variance of mu2 hat. Alright. Is it clear? Okay. So I'll move on to the next one. Okay. So this says that a computer software package was used to calculate some numerical summaries of a sample of data. The results are displayed here. So x is the variable, n is 10, mean is 50, standard error of mean, standard deviation is this, and what will be the variance. Okay. So assuming normality, if x follows normal mu sigma square, then x bar follows normal mu sigma square by n. Okay. So standard error of mean is actually sigma by root n. So this will be 2 by 10, that is 0.2. And standard deviation is given 2. So variance would be 4. So standard error of mean is 1 by 5 and variance is 4. Alright. Okay. So moving on. So this is, let x1 to xn be a random sample with expectation of x is mu and variance of x sigma square. Suppose we use s bar square as 1 by n summation xk square minus n x bar square to estimate sigma square. Find the bias. So for bias, what do we need to do? We need to find expectation of s bar square minus sigma square, and whatever will come, that will be your bias. Alright, you know that x1s are these, and x bar also mean and variance you would be able to calculate, and then it shouldn't be an issue. Okay. Alright. So if you're given a question like this, let x1, x2, x3 to xn be a random sample following IID Bernoulli P. Is x bar the best unbiased estimator of P? Does it attain Cramer-Rao lower bound? So if it does attain, then yes, this is the best unbiased estimator of P. Okay. Is it clear? So in order to find out whether it is attending the Cramer-Rao lower bound or not, what you have to do? So first you have to find out whether x bar is unbiased or not. Okay. So expectation of x bar is expectation of 1 by n summation xi x1 plus x2 plus xn. Okay. Each xi is following Bernoulli P. So this will be 1 by n into summation I equal to 1 to n into P. So this will be P. So x bar is unbiased. That is okay. Now variance of x bar is how much? Variance of x bar is 1 by n square summation variance of xi I equal to 1 to n, because it's a random sample and it's independent. So this will be np by np into 1 minus p by n square. So it will be p into 1 minus p by n. Okay. Now, in order to find out the Cramer-Rao lower bound, we need to first find out the information. Okay. So IP is actually expectation of del theta log fx x given theta square given p. That we can write as minus of expectation del theta square log of fx x given theta. So how do we find this out? First we have to find out for each element what is fx x given theta. Alright. So here, since xi's follow Bernoulli P, it means xi is 1 with probability p and xi is 0 with probability 1 minus p. So we can write fx x given theta or p as p to the power x into 1 minus p to the power 1 minus x. So when x is 1, the probability is p. When x is 0, the probability is 1 minus p. Okay, so this entire thing is captured by this expression. Now if we take a log of fx x given p, we'll land up at x log p plus 1 minus x log of 1 minus p. Okay. Now what do we do? Now we differentiate with respect to p. Del p of log of fx x given p. So this will be x by p plus 1 minus x by 1 minus p, and here we'll have a minus thing. Okay. So now again we'll have del square del p2 log of fx x given p. This is how much? This is d dp of x by p minus 1 minus x by 1 minus p. Okay. So this is what? Minus x by p square minus 1 minus p whole square. This will be 1 minus p into, with respect to p, so it will be 0, minus of 1 minus x into minus 1. So then this will be minus x by p square minus 1 minus x by 1 minus p whole square. Okay. So then for one variable, for x bar, when ip is how much? The Cramer-Rao lower bound for x bar should be what? That should be, so what are we estimating here? Our g theta is actually p, and I theta should be minus n expectation of del 2 del p square log of fx theta, x given theta. Okay. So this one is minus n into this part we have already calculated, and that is this thing, expectation of, this is what? Minus x by p square minus 1 minus x by 1 minus p whole square. Okay. Sorry, x capital here. So we'll write it as minus n into expectation of, this will be minus of p by p square. Since x follows Bernoulli p. Okay. And minus of 1 minus p whole square. This will be 1 minus expectation of x is again p. So what do we have here? We have minus n minus 1 by p minus 1 by 1 minus p. So what do we have? N into n into 1 by p plus 1 by 1 minus p. So this will be n into p into 1 minus p, 1 minus p plus p. So this is actually n by p into 1 minus p. Okay. So this is my I theta. Alright. So I got my I theta as n by p into 1 minus p. G theta is how much? G theta is p. So g dash theta square is equal to 1, because this means d dp of p and then square of that. Alright. So then this is 1. Therefore CRLB is 1 by I theta, and that is 1 by I theta is how much? N by p into 1 minus p. Now this is matching the variance of x bar that we had already calculated. Okay, here. Where is it? Here, see, variance of x bar is p into 1 minus p by n, and that is matching our CRLB. So then the answer is that yes, x bar is the best unbiased estimator because it attains CRLB. In the class of unbiased estimator, x bar is the best because it attains the lowest variance. Is it okay? So whenever you are asked about the Fisher information criteria or x bar, first just steps are, step 1 is to write the PDF. Okay, x1, x2, xn is your random sample. So just take, if it is IID, just take one xi and write the PDF. Okay, then that would be your fx given theta, x given theta. Then step 2 would be take log. Okay, so log of fx given theta, x given theta. Then step 3 is del theta of log fx given theta. Okay, and then step 4 is do a double differentiation, log fx given theta. Okay, once you are done with this, then calculate I theta. I theta would be minus n into expectation of this one that you got with one variable. Okay, so del theta square log of f of x given theta, x given theta. Okay, and then you find out g theta, what are you estimating, and then g prime theta whole square by I theta is going to give you your CRLB. And then you have to see if it is equal, it should be less than or equal to the variance of any other unbiased estimator. Y, where y is unbiased. And if it matches, if the variance of y matches CRLB, then y is the best estimator. Is it okay? And any doubts? Alright. So I think I have covered almost all the topics that were discussed during week 10. If there are any queries, you can put a mail. If not, then I'm going to close today's session and I'll see you next week. Thank you so much for joining. Thanks a lot. Bye bye.